Okay, so what we managed to do at this point, we discussed the general definition of a machine learning problem and what is it that we're trying to accomplish here. And the very first cost that we're going to consider is known as a least squares cost. So let me talk about it and illustrate exactly what is meant by that. So when you look at the least squares cost, it is sometimes called least squares deviation, etc., etc. It is defined according to this formula over here. Now, what is usually meant by this is, I mean, it's easier to understand how least squares deviation cost is introduced is if you look at, again, yet another example here. So I'm going to pick, say, again, another data set. I'm assuming that this is my set of training examples. And suppose that I'm fitting a response surface that looks like this. And we're dealing with the regression problem. In the regression setting, the h of x itself is interpreted as a prediction of y. So concretely, what it means is that, let's say if I focus on this observation over here, then this is, of course, the value of my univariate feature vector x sub I. But what is more interesting is that this value on the vertical axis is my observed y sub I, whereas this value here is my predicted response, h of x sub I. And as you can see, there is a little bit of an error here. What I observe is different from what I predict. And it is this difference between y sub I and h sub I and h of x sub I that is used as the prime element of this least squares deviation cost. Now, this quantity here, y sub I minus f sub I, h of x sub I, is also known as a residual. And also notice that this residual is squared. So the residual itself could be either a positive or a negative, but once we use it inside of the least squares deviation cost, it is always squared. Therefore, all of these terms under the sum is positive. And also notice the presence of this kind of normalizing factor 1 over n, because we are summing up all of the residuals over the available data set or set of examples 1 through n. This normalizing factor kind of brings it back to the individual record level. And then sometimes people even go even further and take the square root of this, but for the purposes of our discussion, this is somewhat irrelevant. Now, the nice thing about this having this scaling factor is that when you have different data sets with different numbers of examples, and you calculate least squares deviation cost in those data sets, then you can easily judge at least some rough agreement performance-wise, whether you have a good performing models or you have bad performance in different data sets. Least squares deviation cost sometimes is also known as mean squared error. There's also conceivably other ways to call it, but the point is that it is always a squared residual that enters into the definition of the mathematical definition of the cost function. And again, to remind you, the purpose of data mining algorithm, machine learning algorithm, is to minimize cost. So we are looking at the measure of the goodness of fit here. Now, what can be said about least squares deviation cost? Well, it has a nice mathematical properties, and that's probably why it's one of the historically the earliest available cost functions. The nice thing about it is that if you look at the formula, it's a nice analytical function. So, for example, if you parameterize the hypothesis as a linear combination of axes, then you have essentially a quadratic form here, nice convex function. And if you take the derivatives, you will get nice systems of linear equations and so on and so forth. So the least squares deviation cost kind of natural from the mathematical point of view, and it's the simplest, and it always arises in concepts like a linear regression, for example, or even support vector machines, and so on and so forth. So the least squares cost has a nice mathematical characteristics, but what's more interesting is it also has a nice statistical properties. The next little section is more like a detour into the, for some of you, an obscure world of statistics. But for those of you who can appreciate the power of statistics, it's kind of interesting to see how least squares deviation cost can be derived based on one of the fundamental principles in statistics, generally known as the maximum likelihood principle. And again, so don't worry if you don't get the exact meaning of what I'm about to do now. At least it's useful to keep that in mind. So suppose we wanted to find the solution to this problem from some kind of statistical point of view. Then what we would start with is by introducing the concept of a conditional distribution of y given x. Because the supervised learning problem essentially can be boiled down in statistical terms as the problem of finding a conditional distribution of y given x. And that's what I'm going to write here. I'm going to write a PDF, or a conditional distribution of y given x, where f stands for probability density function. And under so-called standard normality assumptions, what we are going to do here, we are going to assume that the conditional distribution of y given x is governed by Gaussian or normal distribution. So if I skip all of the normalizing constants, the root matter is that it's e to negative y minus h of x divided by sigma all squared. So basically what I'm saying here is that under standard normality assumptions, the conditional distribution of y given x is normal with constant variance. So this sigma is constant. And h of x normally is described as mu. That's the conditional mean of the distribution. So what I'm saying is that my statistical model imposes essentially the assumption that at every given x, the distribution of y is normal with the same constant variance or standard deviation, and the only thing that changes is its mean, and that happens to be the response surface that I'm interested in finding. Now, applying likelihood principle to this kind of setup on a data set under IID assumption, I can calculate a log likelihood simply as a log product I goes 1 through n. And again, I'm skipping all of those normalizing constants. They're irrelevant. E to negative. And here I apply this to the data set. Y sub I minus h of x sub I divided by sigma all squared. Now, maximizing likelihood is the same as maximizing log likelihood, is the same as minimizing negative log likelihood. And because we want to eventually arrive at the cost function, it's useful to introduce negative log likelihood. But now if you take this expression here and simplify it, and again, ignore all of these extra constants, etc., what it boils down to is that the log of product is a sum of logs. Log and exponent cancel each other, minus and minus cancel each other, and we essentially arrive at the formula, which is sum I equals 1 through n of y sub I minus h of x sub I squared. And this is exactly the j function that we introduced over here. So as you can see, when I say that the least squares cost has a nice statistical properties, that's exactly what I mean. It naturally arises under standard normality assumption, and this is how usually all of the regression texts start with. They introduce those assumptions and proceed by explaining all of the statistical foundations of it. Is this an ideal loss? Unfortunately, no. And what happens is that the least squares deviation loss has a known issue, and that is the issue of outliers. Now, what's an outlier? Suppose I have an observation here that is kind of out of sync with everyone else. Maybe it's been mislabeled, maybe it's being, it belongs to a different data set, Who knows? But it may always sneak into the data set. So in this case, what happens is, if this is x, my x sub I, and we already know that this here is what I predict, and this is my observed value. So in this case, the residual is very large. You take a large residual, you put it in a square, and you may end up with a nasty situation when the entire loss function will be dominated by a few large residuals that are attributable to outliers. And that is what's usually meant by problems with outliers, and this is a kind of issue that needs to be addressed. So we introduced least squares loss as the most historically kind of convenient loss. It has a nice number of all sorts of properties, but unfortunately it has an issue with outliers. So what we're going to do in the next video, we'll start with this, and I will show how a different loss can be introduced in the regression case that addresses this issue of outliers and makes things, introduces some kind of robustness into the problem of estimating the model performance.